Sink into an ocean depth where light is less a feature and more a rumor. The dark down here is not simply black, it is the sensation that the world has been muted. Water presses in from every direction, steady and immense, the kind of pressure that makes metal creak and confidence evaporate. In that near silence there is a slow rhythm, a pulse you feel more than hear, as if something ancient is moving through the water on purpose. Then the void snaps into color. Red blooms into yellow. A pale shape hardens into mottled brown. Smooth skin lifts into jagged spikes, then relaxes into rippling sand. In less time than a blink, the seafloor gains and loses, a creature like a magic trick performed by geology itself. If this turned up in a rover photo from Mars, someone in a serious jacket would call it evidence of extraterrestrial life, and the rest of us would immediately argue over its name and its logo. That is the octopus problem. Not because octopuses are villains hunting humans, most would rather vanish than fight. The problem is that they refuse to fit the neat boxes that make people comfortable. An octopus is not merely smart, it is a separate branch of intelligence, a parallel experiment in consciousness that took a wildly different route from ours. Vertebrates built a central command center, packed decision-making into a skull, and wired the body to follow orders. The octopus built a distributed system, a nervous parliament spread across the body, where the arms do real thinking and the brain is more of a coordinator than a dictator. Start with the headline number. A typical octopus carries around 500 million neurons, enough to place it in the same broad neighborhood as some mammals people casually call clever. The twist is where those neurons live. In humans, most are clustered in the brain. In an octopus, about 2/3 are distributed through the 8 arms. That is why it is often described as having 9 brains. One central brain, plus 8 major nerve hubs in the arms, each capable of serious processing. It is less a single mind in a skull, and more a networked mind in motion. Those arms are built for a world of cracks, caves, and coral mazes. The suckers are the secret weapon. They are not merely suction cups, they are sensory organs. They taste and touch at the same time, reading the chemistry of a surface like a tongue reads flavor, and reading texture like fingertips. An arm can slip into a crack you cannot see into, explore a maze of rock, and make quick choices without waiting for headquarters to approve every turn. That is why an octopus can look unsettlingly capable. It is not thinking in one place, it is thinking everywhere. Distributed intelligence changes coordination too. Human hands do not hold side meetings without the brain. Everything routes through the central office. An octopus can pass information through neural pathways that reduce the need for the central brain to referee every movement. The result is a creature that can handle several tasks at once. One arm scouts, another pries, another steadies the body, another tastes the current. The central brain sets a goal, and the arms negotiate the details like a team that trusts each other. Now add blood that looks like it belongs in a science fiction prop department. Humans bleed red because our blood uses iron-based hemoglobin to carry oxygen. Octopuses use copper-based hemocyanin, so their blood runs blue-green when oxygenated, the color of antifreeze with ambition. They move that blood with 3 hearts. 2 smaller hearts pump blood through the gills to load up on oxygen. One larger heart sends it through the body. It is a clever arrangement for life, where oxygen can be patchy and the sea never promises stability. There is, however, a wonderfully awkward catch. When an octopus swims by jet propulsion, that central heart can stop beating. Swimming is so demanding that the animal has to choose between top speed and full circulation. That is why octopuses often prefer to crawl, using 8 thinking arms like a living rover. It is not laziness, it is energy budgeting. The octopus looks like a superhero and behaves like an accountant, which is, frankly, a combination that tends to survive. Then, comes the skill that makes the animal feel genuinely otherworldly: camouflage. An octopus can change color, pattern, brightness, and even texture in about 1/5 of a second. Chameleons get the publicity, but octopuses operate on a different timetable. This is neural control, fast and precise, like a display system wired directly into the skin. The seafloor stops being a place it sits on and becomes a costume it wears. Chromatophores are tiny pigment sacs wrapped in muscles. Tighten them and reds, yellows, browns, and blacks flash into view in millisecond pulses. Beneath them sit iridophores that bend and scatter light into shimmering blues and greens. Beneath those are leucophores that reflect ambient light, helping the animal match the overall brightness of its surroundings. Then the skin adds a final flourish: papillae, muscular bumps that rise and fall, turning smooth skin into rough rock, barnacle crust, or coral like spikes on command. And here is the twist that makes it stranger. Many octopuses do not see color the way humans do, yet their camouflage can be absurdly accurate. One clue lies in the skin itself. Octopus skin contains light-sensitive proteins similar to those found in eyes, and the skin can respond directly to light, feeding information to the color-changing machinery without waiting for the brain to approve. It is as if the body senses brightness and shadow across its surface and adjusts automatically, like smart curtains closing before anyone notices the room is exposed. Some species take camouflage and turn it into theater. The mimic octopus from Indonesian waters does not just disappear, it performs. Faced with one predator, it bands its arms and moves like a venomous sea snake. Faced with another, it flares its limbs to imitate the spines of a lionfish. On open sand, it can flatten itself and glide like a flatfish, an impression so convincing, it feels like the ocean is doing impressions of itself. The point is not only that it can change shape, the point is that it can choose a disguise that fits the danger in front of it, and that choice looks less like reflex and more like judgment. Another species delivers a different kind of shock: the coconut octopus. It has been observed carrying halves of coconut shells or other debris across open sand, essentially the ocean version of crossing a brightly lit car park with no cover. It does it anyway because it is transporting a portable bunker. When danger arrives, it assembles the pieces into a shelter and tucks inside. That is tool use. That is planning. That is delayed gratification. It is a mollusk doing architecture, and it quietly embarrasses a long list of animals with sturdier reputations. The weirdness goes deeper than behavior. The octopus also plays an unusual genetic game. Most organisms adapt through random changes in DNA passed down across generations, a slow process measured in long stretches of time. Octopuses and their cephalopod relatives have an extra dial: extensive RNA editing, especially in nervous tissue. RNA is the working copy that carries instructions from DNA to the protein-building machinery. By editing RNA at huge numbers of sites, an octopus can fine-tune how certain proteins behave without rewriting the underlying DNA blueprint. When conditions shift, such as changes in temperature, this system can help adjust neural performance quickly, more like tuning an instrument than rebuilding the orchestra. This is not a modern party trick. The octopus story is a deep-time epic. Roll back to the Cambrian explosion more than 500 million years ago, when Earth's oceans were a chaotic laboratory of new body plans. Early cephalopods emerged into those seas, while our own distant ancestors were still tiny creatures hiding in mud. Over the next 500 million years, through extinctions, shifting continents, and changing currents, the cephalopod line refined its senses, its movement, and its nervous system until it produced a boneless animal that solves problems for a living. And then, just as the story starts to feel like a celebration of intelligence, nature delivers the darkest twist. Many octopus species reproduce once and die. After a female lays her eggs, she becomes their guardian, cleaning them, blowing water over them to keep oxygen flowing, and defending the den with a devotion that looks almost tender. Then, she stops eating. At first, it resembles focus, the way a parent forgets their own needs. Then, it becomes clear that a switch has been flipped. Her body declines beyond what starvation alone would explain, and behavior can turn disturbingly self-destructive, as if the animal is being driven by a program it cannot override. A small gland near the eyes, the optic gland, helps orchestrate this process. After egg-laying, it triggers cascades of hormones and chemical signals that alter appetite, metabolism, and behavior, steering the mother toward death. In experiments, when researchers removed the optic gland, brooding females could abandon the eggs, resume feeding, and live far longer. The death is not an accident. It is built into the design, an evolutionary instruction written into the biology of a creature capable of problem-solving, deception, and surprisingly gentle care. The reason is brutally practical. Octopuses are opportunistic predators, and cannibalism is a real risk. If mothers survive to see hatchlings emerge, some would likely eat their own young. The species protects its future by ensuring the present generation does not remain to consume it. By the time the eggs hatch and release a drifting cloud of tiny octopuses into the water, the mother is usually gone, her body returning to the ecosystem as nutrients. The ocean absorbs the loss and carries on, because in nature, even tragedy is part of the workflow. So the octopus stands as proof that intelligence is not a single ladder with humans smugly at the top. It is a landscape with multiple peaks, and some of those peaks look alien to us. A creature with 9 brains, blue-green blood, 3 hearts, skin that senses light, arms that think, and a genetic toolkit that can be edited on the fly forces a simple realization: the rules people take for granted are not rules at all. They are habits. Somewhere below the last reach of sunlight, that lesson is still quietly moving through the water, wearing the sea floor like a costume, and living as if the universe is wider than our favorite explanations.